Good morning, all of you. Welcome to Sri Jayendra Rank Zone. In the previous lecture, we have completed metallurgy. Now we are going to start new chapter, that is coordination compounds. Very important for all competitive exams. Definitely, you will get 2-3 questions from this chapter. So, starting onwards, listen carefully, and whatever the PPTs have been screen shown to you, you have to please make a note in the classwork. If you maintain classwork, then only you can understand it better. So right now we are going to start coordination compounds. Very important chapter for JEE mains, NEET and advanced. Any type of competitive exams. Without this chapter, there will be no question. So that's why it's very important. Please note it down. And whatever we are discussing, whatever slides are displaying on the screen, please make it as classwork. So right now we are going to discuss now. Let us start now. First one, introduction to this concept. Molecular addition compounds. Molecular addition compounds. So we are going to discuss now. So what are molecular addition compounds? When a solution containing two or more simple salts is evaporated to dryness. So when a solution containing two or more simple salts is evaporated to dryness, crystals of molecular addition compounds are formed. What are formed? Crystals of molecular addition compounds are formed. So based on the nature of the compounds, these molecular addition compounds are divided into two types. One is double salt and there is complex salts. In this chapter, we are going to discuss about complex salts or coordination compounds. Very important. So how this coordination compound has come into existence? When a solution containing two or more simple salts, it is evaporated to dryness. Crystals of molecular addition compounds are obtained. So based on the nature of the compound, these are divided into two types. One is double salts and there is complex salts or coordination compounds. And these coordination compounds, usually they are found by D block elements. Why D block elements are formed coordination compounds? Because they have expanded octet. They can expand their octet. Since they can expand their octet, they can form complex compounds. Since they can expand their octet due to the availability of d orbitals, they can expand their octet due to the availability of d electrons. So that's why most of the coordination compounds are formed by d block elements. So d block elements are the basis for the formation of complex compounds or coordination compounds due to the they can expand their octet. So this is about introduction of this concept. When a solution containing two or more simple salts is evaporated to dryness, crystals of molecular addition compounds are obtained. So these molecular addition compounds are divided into two categories. One is double salt and there is simple salt. So that is coordination compounds. Let us see now. So what are double salt? These molecular addition compounds are stable only in solid state. First point. So double salts are stable only in solid state. In solution, they dissociate to give the same ions as that of the constant salts. In these very important point, this point is very important. Please note down. These compounds lose their identity in solution state. These properties are the properties of these salt is same as the ions of the constant salts. Example, potash alum. Potash alum is used for purification of water. So alum is used for, this is also called as alum. So it is used for purification, is used for purification of water. Alum. It is also called a double salt. Double salt means it contains two salts. One is purification of water. So potassium sulfate, aluminum sulfate, dot 24H2O. So water of crystallization. Next, more salt. It is also very important salt. It is used for the estimation of compounds. So ferrous sulfate, ammonium sulfate, dot 6H2O. This is called more salt. Even the formulas also they are important. So in these, what happens? These compounds lose their identity in solution state. Means these compounds does not have the character of iron, sulfate, or nitrogen, or potassium or sulfur or aluminum. So they lose their character. So in these compounds, the elements lose their identity. These compounds lose their identity in solution state and they form chemically. They form by the means of chemical combinedness. So this is called double salt. So what are double salts? These molecular addition compounds are stable only in a solid state. In solution, they dissociate to give the same ions. Means, for example, when you dissolve potash alum in water, what happens? It forms potassium ions, sulfate ions, aluminum ions, along with H plus ions and OH minus ions. so as that of the constant salts. These compounds lose their identity in solution state. The properties of these salts is same as those of ions of the constant salts. So whatever the salt is having the properties same. So this is called double salt. Next continuation. Complex salts are coordination compounds. These molecular addition compounds will retain their identity in solid state as well in solution state. This point is very important. So the complex compounds will retain the elements in the compounds will retain their identity as well as in solution state as well as in solid state. So these compounds when dissolved in aqueous solution do not give the same ions as that of constant salts. They do not give the same ions as that of constant salts. The properties of these salts are different when compared with the constant ions. When compared with the constant ions, the properties are different. Means, for example, for potassium ferrocyanide will neither have the property of potassium or iron or cyanide. So it will have different properties. Copper ammonium sulfate, it neither has the property of copper or ammonia or sulfate ions. So that's why the properties of these salts are different when compared with constant ions. So example for coordination compounds, potassium ferrocyanide K4FeCN taken 6 times and copper ammonium sulfate CuNH3 taken 4 times sulfate. So this is called IUPAC names we will be discussing later on, but here just normal name we have done. So these are nothing but complex salts are coordination compounds. What are complex salts or coordination compounds? The molecular addition compounds, when evaporated, forms crystals. So these crystals are divided into two types. One is double salts and there is coordination compounds. So these are nothing but molecular addition compounds. And in coordination compounds, the molecular addition compounds will retain their identity in solid state as well as in solid state, where double salt will not retain their identity. So that's why this point is important. These compounds, when dissolved in aqueous solution, do not give the same ions as that of constant salts. For example, you can see here, potassium ferrocyanide, when dissolved, what happens? It forms 4K plus FeCN taken 6 times minus. So this is the scenario. So potassium will be separated, iron cyanide will be formed. Like that, it will form. So that's why the properties of these salts are different when compared with constant ions. So it has neither the property of potassium, neither the property of iron, neither the property of cyanide. Whereas in salts, it has their own properties. Next continuation. Basic terminology in coordination chemistry. So now we are going to discuss, as I told you, in this chapter, we are going to discuss more about coordination compounds. So you should know the basic terminology, that is basic terminology in coordination chemistry. First one is coordination identity. What is coordination identity? A coordination identity constitutes a central metal atom, very, very important. It consisting of central metal atom or ion bonded to a fixed number of ions or molecules. So this is called as coordination entity. So cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. So this total bracket one, the substances, the compounds which are present in brackets are nothing but coordination entities. We can say the substance represented in brackets, represented in brackets, the square brackets. So you can say square brackets are called coordination entity. Coordination entity. So that is called coordination entity. Very, very important. Next continuation. Second term, central metal atom or ion. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is known as central atom. So potassium ferrocyanide in this Fe plus 3 is a central atom, not the potassium. Only Fe plus 3 is the central atom which is present in coordination entity. So in a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a geometrical arrangement, in a definite geometrical arrangement around it is known as central atom. So here Fe plus 3 is called central atom or ion. These central atom or ions are Lewis acids, very, very important. They can accept electron pairs. Lewis acid means what? They can accept electron pairs. Lewis acid means they can accept electron pairs. They can accept electron pairs as the active electron pairs from the ions or groups. So this way, this plus 3 is there, so it is ready to accept electrons. So these are nothing but central metal atom. I hope you understood what is central metal atom. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement. Very important. They have the fixed shape also. So definite geometrical arrangement around it is known as central atom. It is known as central metal atom. Usually they consisting of metals. And in this, the central metal atom are nothing but they are nothing but Lewis acids because they can readily accept electron pairs. They can accept electron pairs easily. So that's why they are called as Lewis acids. Next continuation. Ligands, very, very important. The negative ions are neutral molecules. Here, important point. The negative ions are neutral molecules which are coordinately bonded to, means they are bonded by the means of coordinate covalent bond. Coordinate covalent bond. One is donor and there is acceptor. So the ligands are donor atoms, coordinate covalent bond. How they are combined with the metal or central metal atom by the means of coordinate covalent bond. That's why which are coordinately bonded to the central metal atom in the coordination entities are called as ligands. Ligands are electron pair donors and hence they are also called as Lewis bases. So ligands are nothing but the group of atoms surrounding with the central metal atom. The negative ions are neutral molecules or positive molecules which are coordinately bonded to the central metal atom in the coordination entity are called as ligands. Ligands are electron pair donors and hence they are called as Lewis bases. So we have either the negative ions or neutral molecules as ligands. Negative ions are neutral molecules as ligands. Very, very important. Please note it down. Continuation. So these ligands are how they are bonded with the central metal atom. They are bonded to the central metal atom by the means of coordinate covalent bond because central metal atom is nothing but acceptor and the ligands are donors. So ligands, donor of electron pairs and central metal atom are acceptors of electron pairs. So that's why they combine together to form a compound and that compound is kept in coordination entity, that is square brackets. Next types of ligands, very important. So on the basis of charge on ligands, first on the basis of charge on ligands, we have negative ligands, that is F minus, Cl minus, OH minus, Cn minus, S2O3 minus. So we'll call it as fluoro, hydroxy, and cyano, that is cyanide, S2O3 thio, and C2O4 carbon, this is oxalate. C2O4 2 minus is called what? Oxalate. C2O4 2 minus is oxalate. Oxalate ions. S2O3 minus is thio ions, thio, and CN minus is cyano, that is nothing but cyanide, or you can say cyano, and OH minus is hydroxo or hydroxyl, and chloro and fluoro. So we can say now what are neutral ligands? So first one you have negative ligands on the basis of charge on ligands. Second one you have neutral ligands, that is carbon monoxide, water, ammonia, ethylamine, that is RNH2. RNH2 is alkyl amine. These are all considered as neutral ligands. So just note it down, neutral ligands. So neutral ligands we have R, RNH2, NH3, COH2O. All these are called as neutral ligands. Even EDTA also is also a neutral ligand. EDTA is also a neutral ligand. Next we have cationic ligands or positive ligands. NO plus, N2H5 plus, etc. These are all called cationic, nitroxo. So these are nothing but ligands. So ligands are classified into three categories: cationic ligands, anionic ligands, and neutral ligands. So these are called as anionic ligands. Anionic ligands, neutral ligands, cationic ligands, or positive ligands. Anionic are negative ligands. Are negative ligands. So what are ligands now? These are nothing but the donor atoms. They will donate the lone pair of electrons to central metal atom. If they donate one lone pair of electrons, it is called unidentate ligand, monodentate ligand. So let us see now types of ligands based on electrons. So based on number of electron pairs donated by the ligand, based on the number of electron pairs donated by the ligand, they are classified into following types. First one, monodentate ligands. These ligands are donate only one electron pair to a central metal atom. So they are nothing but they can donate only one electron pair. So that is nothing but cyanide ion, hydroxyl ion, ammonia, and water. So water is also a neutral ligand. We can see in some cases even this ammonia also, but mainly we have cyanide ion and OH minus. So these are nothing but monodentate ligands. So let us now some more examples I'll write here. Please note it down. NO2 minus, Br minus. NO2 minus is also monodentate ligand. Cn minus already we have done. So these are ammonia and water are neutral unidentate ligand. They are neutral monodentate ligands. Monodentate ligands. So they can be neutral, they can be positive, they can be negative. So that's why if they donate only one electron pair to the central atom, central metal atom, they are called as monodentate ligands. Ammonia and water are neutral monodentate ligands. They will not donate any electron pair. They will not donate any electron pair. So please note down these changes. Next continuation. Bidentate ligand. These ligands donate two electron pairs to the central atom. Example, we ethane 1, 2 diamine. So this nitrogen is having one electron pair. This nitrogen is also having one electron pair. Due to this, what happens? They are ready to donate two electron pairs, first one as well as second one. So that's why they are called as bidentate ligands. Bidentate ligands, we can call it as ethane 1, 2 diamine, EN. In short form, we call it as EN. EN is nothing but ethane 1, 2 diamine. Oxalate C2O4 2 minus. It is also called bidentate ligand because it is 2 minus charge is there because two electron pairs will be donated. Glycinate ion NH2CH2O minus. So this is nothing but bidentate ligands. 1, 10 phenantholene. Phenantholene ligand also here also with nitrogen 1 and here also 1. So that's why they can donate two electron pairs as they are donating two electron pairs. So they are coming under bidentate ligands. They are coming under what? Bidentate ligands, bivalent bidentate ligands. So even carbonate ion also, CO3 2 minus is also a bidentate ligand apart from this. So all these are nothing but examples of bidentate ligands. What are bidentate ligands? These ligands donate two electron pairs to the central atom. Two electron pairs to the central atom. Next continuation. Next, we have polydentate ligands. These ligands will donate more than two pairs of electrons to the central metal atom or ion. So they are nothing but example tridentate ligands. Here three nitrogens. Three nitrogens will have one lone pair. So they are ready to donate one lone pair, two lone pairs, and three lone pairs. So they are ready to donate three electron pairs. As they are donating more than three electron pairs, we can call it as tridentate ligand, or you can say simply as they can donate three electron pairs, we can call it as polydentate ligands. Polydentate ligands. Polydentate means more than two. It can be 3, 4, 5 also. So more than two, we'll call it as polydentate ligands. But they are very few in number. And they can donate more than two pairs of electrons to the central metal atom. Next continuation. So ethylene diamine tetraacetate ion. This is nothing but tetraacetate ion. It can donate 4. So it is nothing but polydentate ion. So it is commonly called as EDTA. Ethylene diamine tetraacetate ion. You can see ethylene means two carbons, diamine means two nitrogens, and for each two in place of two hydrogens we have acetate ion CH2CO minus, CH2CO minus, CH2CO minus, and CH2CO minus. So this is nothing but ethylene diamine tetraacetate ion. Ethylene diamine tetraacetate ion. This is nothing but polydentate ligand. Example for polydentate ligand. Next continuation. Chelating ligand. Chelating means breaking up. So when this is very, very important. What is a chelating ligand? They'll ask in the examinations, entrance exams. So when a polydentate ligand uses its two or more donor atoms to bind a single metal ion to form ring structure, the ligand is known as chelating ligand, and the complex is said to be chelating complex, chelate complex. These chelate complexes are thermodynamically more stable than normal complexes. So more the number of chelating ligands in a complex, more will be the stability of the complex. Very, very important. So what is chelating complex? When a polydentate ligand uses its two or more donor atoms to bind a single metal ion to form a ring structure, the ligand is known as chelating ligand, and the complex is said to be chelate complex. Chelate complexes are thermodynamically more stable than normal complexes. More the number of chelating ligands in a complex, more will be the stability of the complex. Very, very important point. Please note down in your classwork. Next continuation. So these are the main terms involved in the coordination entities. Next, we have types of ligands. Second type, that is ambidentate ligands. These are also very important. What are ambidentate ligands? What are chelating ligands? What are monodentate, bidentate, and polydentate? All the types of ligands are important. If you don't know the ligands, you cannot write the formula easily. So it is a monodentate ligand having more than one donor atoms. It can coordinate only with one donor atom at a time. So can coordinate with carbon atom or nitrogen atom. If it coordinates with carbon, the ligand is known as cyno, and if it coordinates with nitrogen, the ligand is known as isocyano. For example, NC, that is Cn minus, NC minus. If the ligand is donating to nitrogen through carbon, it is called cyno. If the ligand is donating to nitrogen, it is nothing but isocyano. So NC minus is called isocyano, and Cn minus is called cyno. We'll call it as cyno-cyanide. So cyno, isocyano. So if it coordinates with carbon atom, the ligand means if the electrons are going from carbon atom, it forms cyno. So it is nothing but cyno. And if it is coordinates with nitrogen atom, it is known as isocyano. Other examples are thiocyanato, isothiocyanato. See here N minus, it is coordinating to carbon and it is coordinating to nitrogen and it's sulfur and nitrogen. So SCN minus, here M thiocyanato and isothiocyanato. M nitro, nitritro, NO2, and ONO it is nitrito, nitrito N, nitrito O. If it is donating to nitrogen, it is called nitrito N. If it is donating to oxygen, it is nothing but nitrito O. So nitrito O, nitrito N, all the four are very important. So please note down, these are nothing but, so it is nothing but they can donate the ligands which can donate from two atoms, from two different atoms. More than one donor atoms is nothing but monodentate ligand having more than one donor atoms. More than one donor atoms are called as ambidentate ligands. Example, cyanide, isocyanide. Next continuation. So these are nothing but the terms involved in coordination chemistry. Now we'll discuss the rules, IUPAC nomenclature, and more terms about coordination compounds in these slides. So please note it down. So till now we have done two coordination terms, that is ligands as well as coordination entity as well as types of ligands. Now, more terms in coordination chemistry. First, next we have coordination number. The number of ligand donor atoms. Very, very important. What are the coordination number of the metal? So, the number of ligand donor atoms to which the metal is directly attached, bonded in a complex is known as coordination number. It is equal to the number of coordinate bonds formed between central metal atom or ion and the donor atoms of the ligand. How to calculate coordination number for a given complex, we can easily do it. Later on, I'll tell you. But in the definition wise, if you see, it is nothing but it is equal to the number of coordinate bonds formed between central metal atom or ion and the donor atoms of ligand. For example, you can see potassium ferrocyanide. Here, K4FeCN taken 6 times. So K4FeCN taken 6 times. The coordination number is how many ligands are attaching to central atom? 6 ligands. So the coordination number is equal to 6. Coordination number is equal to how much? 6. What is coordination number? It is nothing but equal to the number of ligand donor atoms to which the metal is directly bonded in a complex. E is known as coordination number. It is equal to the number of coordinate bonds between central metal atom ion and the donor atoms of the ligands. So that's why it is nothing but coordination number is equal to 6. So example also I have shown you. So please note down. Next continuation. So example, NH3 taken 4 times plus 2. So coordination number of nickel is 4 because it is attached directly to 4 ligands. That is 4 donor atoms. That is ammonia. Here ammonia is a donor atom. Since ammonia is a donor atom, it is linked directly with 4 ammonium atoms. So coordination number is equal to 4. And platinum hexachloride, that is also 6. So coordination number is equal to 6. And here 3 are there. But since this is En is nothing but bidentate ligand. How much it is bidentate? Since En is bidentate ligand, so three bidentate ligand means nothing but three bidentate ligand means three bidentate means it is donating 6 electron pairs. Means it is donating 6 electron pairs donating. 6 electron pairs donating. So that's why coordination number is equal to 6. Coordination number is equal to how much? It is equal to 6. So this is nothing but examples of coordination number. Please note down in your classwork. Examples of coordination number. Next continuation. The central atom of ion and the ligands attached to it are enclosed in square bracket and is collectively termed as coordination sphere or coordination entity. The ions outside the coordination sphere is known as ionization sphere. So in potassium ferrocyanide, potassium is nothing but ionization sphere and FeCN taken 6 times is nothing but coordination sphere. So you can easily identify what is coordination entity or coordination sphere. So coordination sphere means the substances which are present in the brackets, square brackets. So the central atom and the ligands attached to it are enclosed in a square bracket. They are enclosed in what? They are enclosed in a square bracket and is collectively termed as coordination sphere or coordination entity. Coordination entity is also same. Coordination entity is also same. It is also called as coordination entity. As I told you in the first case itself, it is also called as coordination entity. So this is nothing but sphere. So example, potassium ferrocyanide, here FeCN taken 6 times is nothing but coordination sphere, and 4K plus, that is potassium, is called ionization sphere. So a complex compound is a combination of ionization as well as coordination sphere. It may or may not be, depending on the type of complex. Next, coordination polyhedron. The coordinate bonds found between the central metal atom. The coordinate bonds formed between the central metal atom or ion and the ligands are directional in nature, which gives a specific geometrical shape for the complex. This spatial arrangement of the ligands atoms which are directly attached to the central metal atom or ion to give a regular polyhedron is known as coordination polyhedron. The most common polyhedrons are, we have most common polyhedrons, let us see now. Octahedral complex, tetrahedral complex, square planar complex. So it is nothing but octahedral complex, tetrahedral complex, and square planar complex. Examples: octahedral, it has coordination number is 6. So cobalt, that is CO NH3 taken 6 times plus 3. Here CO should be small. Here O should be small. That is CO, cobalt. Cobalt NH3 taken 6 times 3 plus is nothing but octahedral complex, tetrahedral complex, and square planar. So in this cobalt NH3 taken 6 times, there is in octahedral manner. So in all these 6, it is surrounding by cyanide ions. Sorry, ammonia. Here we can take ammonia. Here ammonia, 6 ammoniums. Ammonia, 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 and so on. So like that, you'll get coordination entities. Tetrahedral, square planar. So these are nothing but coordination polyhedron. Coordination polyhedron. So this type of geometrical shapes are nothing but coordination polyhedrons. Very, very important next terminology. The oxidation number of the central atom in a complex is defined as a charge it would carry if all the ligands are removed, along with the electron pairs that are shared with the central atom. Example, oxidation number of copper in CuCN4 taken 3 minus is +1, because here copper is in +1 state, because I'll show you now here how we got this +1. So Cu is there. Let us say oxygen state of central atom is X, plus cyanide ion is -1. So plus -1 into 4. -1 into 4 is equal to -3, because -3 is the charge. So X minus 4 is equal to -3, implies X is equal to -3 plus 4. It is equal to +1. So copper oxygen state is +1. And it returns Cu1 and it returns Cu1. In this way, we'll calculate oxygen state. So whatever the coordination entity, we have to take the complete coordination complex we have to take. For example, potassium ferrocyanide, if you take into consideration K4 FeCN taken 6 times. So what is the oxygen state of iron here? So it is potassium is +4 plus iron is X -1 into 6 is equal to, there is no charge, so it is equal to 0. So 4 minus 2, 4 minus x, sorry, 4 plus x minus 6 is equal to 0, means x is equal to +2. X is equal to how much? +2. So in this way, we will calculate oxygen state. So the oxidation number of the central atom in a complex is defined as a charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. Example, oxidation number of copper in this CuCN taken 4 times minus 3 is plus 1 and it is in a Cu1. Here potassium ion in it is iron 2 Fe 2 in Roman number. So as it is in plus 2 state, we will call it as Fe2. So this is called oxidation number of central metal atom. What is this called? Oxidation number of central metal atom. Next, types of complex. We have two types of complex. Complex in which a metal is bound to only one kind of donor atom. It is bonded to only one kind of donor groups or ligands are known as homoleptic complex. You can see here ammonia, here cyanide. So these are all called as homoleptic complexes. Homoleptic complexes means the complex in which a metal is bound to only one kind of donor groups or ligands. The metal is bound to only one kind of donor groups or ligands are known as homoleptic complexes. Example, cobalt hexamine, iron hexacyano, etc. These are all called homoleptic complexes. Next continuation. The complexes in which a metal atom is bound to more than one kind of donor groups or ligands are known as heteroleptic complexes. They are called as what? Heteroleptic complexes. Example here you can see here the copper atom is linked to ammonia as well as Cl. Here the chromium atom is linked to water as well as bromine. So two types of donor atoms, two types of ligands, two different ligands. Actually, we cannot say two types of ligands. We'll say it is two different ligands. Two different ligands. So here also we have two different ligands. Two different ligands. Not only two, it can be more than two also. So complexes in which a metal is bound to more than one kind of donor groups or ligands are known as heteroleptic complexes. Heteroleptic complexes. I hope you understood clearly. Next continuation. So next we'll start with that is nothing but how to write nomenclature, that is coordination compounds nomenclature, very important. So we have done only up to terms in the coordination compounds. Now we'll discuss nomenclature of coordination compounds. Let us see now how to write names of coordination compounds, very important. So let us see now nomenclature of coordination compounds. The formulas and names adopted for coordination compounds are based on the recommendations of the IUPAC, that is International Union of Pure and Applied Chemistry. International Union of Pure and Applied Chemistry. So many of you know that. So formulas of mononuclear coordination entities. These are rules. All the rules are very important. Please note down, write each and every rule and try to apply, because from the naming of coordination compounds, definitely you are going to get one question for entrance exam. For naming of coordination compounds, any type of entrance exam, you will get a question. So that's why you listen carefully all the rules. If you don't understand the rules, you cannot write the names of the compounds easily. So all the rules are very important. So in the following rules are applied while writing the formulas. Rule number 1, the central atom is listed first. The ligands are then listed in alphabetical order. So ligands are always, you have to write the ligands in alphabetical order. The central atom is listed first. The placement of ligand in the list does not depend on its charge. Next, polydentate ligands are also listed alphabetically. So in case if a metal is attached to two or more different ligands, they are written according to the names, that is according to the alphabetical order. For example, if a metal atom, for example, here chromium is there, so it is linked directly with water as well as bromine minus as well as cyanide minus. So if you say like this, for example, then chromium, this is aqua, we'll call it as aqua. This is called as bromo. It's called as cyano. So since three ligands are there, we got it in alphabetical order. So 5 aqua, that is penta aqua, 1 bromo, 1 cyano, chromium. Like this we have tried. So anyway, we are going to learn that. So the ligands are then listed in alphabetical order. First point, the placement of ligand does not depend on its charge. Polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand. and the second in the alphabetical order. So aqua is there, AQ is there, and amine is there, AM is there. So we'll give preference to amine. Aqua means AQ. So AQ is not, because second letter is Q, second letter is M. First letter is similar. So in that case, you have to use that. So this is nothing but rules for writing coordination compounds. More rules we'll discuss now. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. Coordination entity is always kept in square brackets. When ligands are polyatomic, their formulas and ligand abbreviations are enclosed in parentheses. Parentheses means the main chain. There should be no space between the ligands and the metal with the coordination sphere. There should be no space between the ligands and the metal within a coordination sphere. For a complex ion, the charge is indicated outside the square bracket as a white superscript like this. The charge of the cation is balanced by the charge of anion always. Next continuation. The following rules are used when naming of coordination compounds. From here onwards, it's very, very important. All these rules are very important. First rule, the cation is named first in both positive and negatively charged coordination complex. Suppose if we have cations as well as negative, for example, here potassium is there, ferro, cyanide is there. So here the ligands are potassium as well as cyano, and this is cation. So we'll say potassium. First we'll start with potassium cation, then followed by negative, that is cyano, that is six cynos are there, hexacyano, ferrate 2. Oxygen state of iron is 2. So this is the name of the compound. So first, I hope you understood. The cation is named first in both positively and negatively charged coordination complexes. The ligands are named in alphabetical order before the name of the central atom or ion. So here it is only one ligand. If there are more than two ligands, we should follow alphabetical order. So example for this, if you had example, here we can say that is chromium. Here we'll say cyanide. Here we'll say Br. Cyanide, hexa, we'll say cyanide 6. And Br, it is nothing but 1. And here we have aqua. So then we'll say aqua, monoaqua, monobromo, monoaqua, monobromo, hexacyano, hexacyano, chromium or chromate. So chromium we have to write finally. So aqua, monobromo, hexacyano means first alphabetical order, second, then third. So we should, the ligands are named always in an alphabetical order before the name of the central atom or ion. Prefixes mono, di, tri, etc. are used to indicate the number of individual ligands. As I told you, monoaqua, monobromo, hexacyano. This is why we kept it as hexa, because it is 6. So the prefixes mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. So that's why this is very, very important. So please note down. Next continuation. So all the three first rules are very important. So first, the cation is named first in both positively and negatively charged coordination complex. The ligands are named in alphabetical order before the central atom or ion. Prefixes mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. Next, when the name of ligands include a numerical prefix, then the term. So if the ligands are more than 2, we will call it as bis, tris, tetrakeys are used, the ligand to which they refer being placed in parentheses. For example, here PHD taken twice, there is no named as dichlorobis, triphenyl phosphine, dichloro, bis, why bis? Because it's monodentate ligand taken twice. So bis, triphenyl phosphine, nickel 2. Oxygen state of metal is indicated by Roman numeral in parentheses, that is brackets after metal. So here the oxygen state of nickel is +2. So that's why we have written 2 by Roman numeral. So these are the main conditions for writing the name of the coordination compounds. If the complex is cationic or neutral or positive, very, very important, cationic or neutral, the metal is named same as the element. If the complex ion is anionic one, then the central metal atom ends with suffix 8. Very, very important point. This is, please note down. If the complex is cationic or neutral, the metal is named same as the element. If the complex is anionic one, the central metal atom name ends with a suffix 8. For example, some metal, the Latin names are also used. For example, here, potassium Fe6. So in this, we'll say the name of this compound is potassium. Anyway, it is 4 is there, but still we'll write only 1 because we'll not apply for metals other than the central atom. We'll not give the numbers. Potassium, hexa, we got 6 fluorine is there. Hexafluoro, ferrate 2. Because why will is 8? Because this is K4 FeF6 decomposed to form. So here I have should not keep gap, so I just change it. FeF6 is there, so this decomposed to form 4K plus FeF6 minus FeF6 minus. So the complex is having negative charge. See, as the complex is having negative charge, it is called anionic complex. Anionic complex. If the complex is having positive charge, it is called cationic complex. And if the complex is having neutral, it is called neutral complex. So for cationic or neutral complex, the metal is named as same as the element. The metal is named same as the element. So let us see, for example, for cationic complex, and next we'll anionic complex I have given. Next we'll see cationic complex. Let us see now. So cationic complex and anionic complex. So let us see now. For example, for cationic complex. Cationic complex. Cationic complex. For cationic complex example, I'll write here. Please note down. CuEn taken twice. Outside it is SO4. So here in this what happens, it changes to En is nothing but it is ethylene diamine. Ethylene diamine is neutral ligand. So complex charge of copper is +2. The complex charge, this is total complex charge is +2. So that's why we can say it is cationic complex. And for this, we'll name the copper as this. So the name of this compound is bis ethylene diamine copper 2 sulfate. What is the name of this compound? Bis ethylene diamine, because En is nothing but what? Ethylene diamine. Ethylene diamine copper 2 sulfate. Copper, we'll call it as cupate, no, copper 2 sulfate. Please see the difference. Copper 2 sulfate. This point is very, very important. So since this compound, it is nothing but for ethylene diamine, no need to keep bracket. So bis ethylene diamine copper 2 sulfate. Why we got copper name, full name of the metal? So if the complex is cationic or neutral, the metal is named as the same as the element. If the complex is anionic one, like in the case, then the central metal atom name ends with suffix 8. So ferrate 2. For some of the metals, Latin names are also used. So this is the complex iron named as ferrate, and here the complex copper is named as copper only. So see the difference. This point is very, very important. If you don't understand this point, you cannot write the name properly. If the complex is cationic or neutral, the metal is named same as the element. If the complex is anionic one, then the central metal atom ends with suffix 8. For some metals, the Latin names are also used. I hope you understood clearly. Very, very important, these 6 rules. Next continuation. Now, the name of the ligand depends on the charge of the ligand. If the ligand is negative ligand, if the ligand is negative, means donor atom is negative, the name of the ligand ends with O. Very, very important this point. So, for example, Cn minus cyno, NO2 minus nitro, Cn minus cyno, NO2 minus nitro. So like that, we have so many examples. So nitrate, NO2 minus, it is nitrito, sorry. NO2 minus, it is nitrito, like that. C2O4 2 minus oxalato. C2O4 2 minus. It is nothing but what? Negative ligand. So it is oxalato. C2O4 2 minus. It is oxalato. Br minus. Br minus. Bromo. So the name of the ligand depends on the charge of the ligand. If the ligand is a negative ligand means it should have negative charge. Like in this case, cyano, nitrito, oxalato, bromo. The name of the ligand ends with the letter O. For positive and neutral ligands, the name is written as it is, with few exceptions like ammonia, it is named as amine. Water is aqua. CO is named as carbonyl. NO is named as nitrosyl, etc. So for neutral ligands, we have to give the name as it is. Ligand, the name is written as it is, with few exceptions like ammonia, we will write it as amine. For ammonia, we will not write ammonia, we will write it as amine. AMMINE. For water, it is named as aqua. For CO, it is named as carbonyl. For NO, it is named as nitrosyl. So these are nothing but amine, carbonyl, nitrosyl, triphenyl phosphine. For example, you can see here C6H5 taken 3 times. P. This is nothing but triphenyl phosphine. Triphenyl phosphine. It is not ending with O. It is as it is. The name is as it is. PPH3 taken twice. So triphenyl phosphine. PH3 phosphine, pyridine, C5H5N. C5H5N, what is I'll call it as C5H5N. It is called as pyridine. So these are nothing but what? Neutral ligands or cationic ligands. So for positive and neutral ligands, the name is retained as it is. The name is retained as it is, with a few exceptions like ammonia is named as amine, water is named as aqua, CO is named as carbonyl, NO is named as nitrosyl. For negative ligands, we'll apply the ligand ends with the letter O. So for cyanide, we'll write it as cyano. For nitrogen dioxide, that is nitrito. And for oxalate ion, we'll say oxalato. For bromine, we'll say bromo minus. So these are the main ligands. I hope you understood clearly. Very, very important these points. So with this, we can say naming of coordination compounds. Now naming of certain ligands, you can see here. This page, if you understand easily, you can do it better. So very, very important. Amine, aqua, carbonyl, nitrosyl, ethane 1, 2 diamine, because nitrosyl, chlorido, bromido, bromo or bromido, chlorido, cyanido, hydroxido, thiocyaneto, nitrito, oxalato, thiosulfato, carbonato, nitrosilium, hydrazinium. So these are all the ligands. For positive ligands, IUM. For negative ligands, O. And or you can say chlorido. Chlorido is better. So chlorido, bromido, bromo, you can write for chloridium or even chloro. Both are same. For bromido or bromo. For cyanido or cyno, as I told you. Maybe you'll get confused. So I told in the previous session, in the same session, we have done chloro, I said. Even this is also correct, this is also correct. So anything you can write R, and R. So these are the ligand names. This is very, very important. Please note down, and you can see the ligand. And this is nothing but hydroxido, or you can say hydroxo, thiacinato. This is correct only. So remaining all the ligands are same. So please note down. This is very, very important. If you know the naming of the ligand, then only it is easy to write the name of the compound. In the examination, they'll give the formula of the complex compound and they ask us to write the name, or they'll give name, they ask us to find the formula also. Anything they can ask. Now let us see example one, how will you get in the examination. Write the formula for the following complex whose IUPAC names are tetraamine aqua cobalt 3 chloride. Tetraamine NH3 taken 4 times. Aqua water, cobalt 3 chloride. So 3 chloride and chlorine, 2 chlorines are outside and 1 chlorine is inside. Potassium tetrahydroxido zincate. Tetrahydroxido. Hydroxido means here the central atom is zinc. So zinc, OH taken 4 times. Potassium, as I told you, even if you are writing potassium 2 also, we cannot write dipotassium. Dipotassium not required. Should not write dipotassium. Dipotassium is not to write. Only will write potassium and even chlorido, trichloride we have. Since chloride is the neutral ligand, so after that it is nothing but so chloride. Very, very important. Next continuation. Next coordination numbers. Dichlorobis. Let us see now. Okay. Dichlorido, bis ethane 1 comma 2 diamine cobalt 3 bromide. So the name of this given. So we have tried the formula dichlorido bis. Dichlorido bis means two chlorines. Bis ethane 1 comma 2. Bis they have given for monodentate ligands here. Bis means if bidentate ligands are more than one. If bidentate, you can write this. If bidentate ligands, bidentate or polydentate ligands are present are present are present for two times we'll call it as bis. For three times tris. If three times are there, we'll call it as tris. For four times it is tetrakis, like this we'll call. So two times it is, so since en is present two times, so it is nothing but bis. Only for bidentate and polydentate ligands. If bidentate ligands are polydentate ligands are polydentate. For polydentate and bidentate only we have this polydentate ligands. So dichlorido, bis, ethane 1 comma 2 diamine, En taken twice, cobalt 3 bromide. Since bromine is outside, we'll say outside we have tried bromide. Tetracarbonyl nickel. So nickel tetracarbonyl. Sodium dicyanide argentate. Sodium Na. Dicyanide Cn taken twice. Argentate 1. So silver is one time. So we can take this in complex and here sign dicyanide, so sodium is 1. So depending on the charge, you can write 4 or 5 or 1 or 2 because since silver charge is 1, this is -2, this should be +1. So only one sodium. Like this you have to identify. Next type of questions. Give the IUPAC names of the following complexes. So they have given CrNH3 taken 3 times, H2O taken 3 times, Cl3. Since we have 3 types of ligands, first point number 1, since 3 ligands are involved, what is this? Amine, water, and chlorine. So water is called as aqua and amine is called as Am. So both are starting with A. In case of 2 or more ligands, we have to see the alphabetical order. And if these two elements are starting with A, so we can take the next letter. That is for amine, it is M, and for aqua, it is Q. So definitely this will come first. So this will come first, and this will come second. So 1 and 2. So since amines are 3, so triamine, triaqua, since 3 aquas are there. Chromium, because this is a cationic complex. Chromium has T's. 3 chloride, because 3 chlorines outside. This becomes +3 and this becomes -3. So that's why 3 chlorine ions. 3 chlorine ions. Very, very important. Since the charge on the outside is -3, so this should be +3. These two are neutral, so this becomes +3. Since it is +3 and this is -1, so as it is cationic complex, since it is cationic complex, it is nothing but chromium as it is. We should not write chromate. We'll write it as chromium. Chromium 3 chloride because since it is cationic complex. Cationic complex. You should understand whether it is cationic complex or anionic complex. If cationic complex is, the metal is named as same. The metal is named as, what is the metal here? Central metal atom chromium. So we'll write chromium only. If anionic complex is there, the metal is named as chromate. So for example, here you see, this is also cationic complex because sulfate is 2 minus. 2 minus is taken 6 times. So this should be 6 plus 6. And so +3 state. How much 3? +3 state. So we can say tris. Why? Because 3 bidentate ligands are there. So tris ethane 1 comma 2 diamine. Tris because 3 times is there. Cobalt, and sulfate is outside. So cobalt, oxygen state of cobalt is +3. So cobalt 3 sulfate. How many sulfates are also not required to count. Next, it is nothing but 2 complexes. AgNH3 taken twice, AgCN taken twice. Is named as diamine silver 1, dicyano argentate 1. Dicyano means two cynos. Diamine means two. Silver one, silver one. In both the complex, it is plus one as well as plus one. So it is named as dicyanoargentate. Argentate why? Because here this is silver as it is because this cation, and this should be anionic complex because this should be minus one. So this is anionic complex, this should be cationic complex. So cationic complex silver and anionic complex is argentate. Argentate 8 is kept here. So because AgCN taken 2 minus AgCN taken twice is anionic, whereas AgNH taken twice is cationic. So in cationic, we have written the silver as the silver, same name of the element. For anionic, we'll end with 8. 8. So here also this is cationic complex and this is anionic complex. So we can say potassium. How many potassiums will not consider as I told you, and outside this also not considered. So potassium hexacyanido or hexacyano federate 2. Why this is federate 2? Because this is anionic complex because this changes to K4 plus FeCN taken 6 times minus this complex is anionic. Anionic means federate. Federate 2. Very, very important. So please note down. This is very, very important. Naming of complex compounds, they'll definitely ask a question. FeCO taken 5 times is named as iron. This is pentacarbonyl iron 0 because oxygen state of iron is 0. For carbonyl compounds, the oxygen state of iron is oxygen state of the metal is 0. As I told you in case of NiCO taken 4 times in the previous chapter metallurgy, the oxygen state of nickel is 0. So we'll say tetracarbonyl nickel 0. Tetracarbonyl nickel 0. Same way here, pentacarbonyl iron 0. Fe4 FeCN taken 6 times 3 is named as, this is again anionic complex. What is this called? Anionic complex. Anionic complex easily you can identify because the cation is outside. So it is nothing but iron 3 hexacyanidofederate 2. Iron 3. Iron 3 means the oxygen state of iron is plus 3 here. So iron 3 hexacyanidofederate 2. Hexacyanido because 6 cyanides are there. Hexacyanidofederate plus 2 because the oxygen state of this is 2. So federate plus 2. Very, very important this compound name. Iron 3 hexacyanidofederate 2. So the name of the complex, definitely you'll get a question. So if you follow the rules properly, 100% you'll get the answer correctly. So now we have discussed this concept, very, very important. So writing naming of compounds is very, very important. So that is very important now. Let us see now. So in the next session, we'll discuss more questions about writing naming of the compounds, how to write naming of compounds. That is very, very important. Naming of coordination compounds is very important. Naming of coordination compounds. More questions we'll do in the next session. Naming of coordination compounds. More questions we'll do the next session. So in this lecture, we have naming of coordination compounds. Very, very important. So please do it properly. And in the next lecture, we'll continue with a new topic apart from questions based on coordination compounds. I hope it is clear. Next session we'll do definitely coordination compounds, questions based on coordination compounds, some more questions about coordination compounds. So first lecture is very, very important. In this lecture, what you have done, we have done already in this lecture, what we have done about what are the terms used in the coordination compounds, introduction of the chapter, as well as naming of ligands and rules for writing the coordination, name of the coordination compound. So these three topics we have done. Next session we'll come up with a new topic, and apart from that we'll do questions also based on this session. Only few questions I have done. More number of questions we'll do definitely. We'll discuss more about cationic complex, anionic complex, and neutral complex. So with this, I'm completing this lecture. So listen carefully and follow. This first lecture is very, very important. Definitely you are going to get one question based on this first lecture. So I request you all to note down in your classwork all the slides, and then you start working out new questions from this concept. Next session will continue. Thank you all.